Space is often described as silent. In movies, explosions echo between stars and engines roar across the vacuum. But in reality, outer space contains almost no air. Sound, as we normally understand it, requires a medium. It needs molecules to vibrate, to carry waves of pressure from one place to another. On Earth, sound travels through air, water, or solid ground. But in the vacuum of space, there are almost no particles to transmit these vibrations. That means that if you were floating unprotected between the stars and something exploded nearby, you would see the flash of light long before you would hear anything at all. In fact, you would hear nothing. Yet the story does not end there, because while space is silent in the traditional sense, the universe is far from quiet. It is filled with vibrations, oscillations, and waves, just not in the form our ears are designed to detect. In interstellar and intergalactic space, there are regions filled within gas and plasma. These environments can support pressure waves similar to sound, though at frequencies far beyond human hearing. Galaxy clusters, for example, contain enormous amounts of superheated plasma. When supermassive black holes at the centers of galaxies release energy, they can create ripples through this plasma. In one famous observation, astronomers detected pressure waves in the Perseus galaxy cluster that correspond to a note far below the lowest tone humans can hear. If translated into audible frequencies, it will resemble a deep, continuous hum echoing across millions of light years. The idea that black holes can produce sound is not poetic metaphor. It is a physical description of pressure waves traveling through cosmic gas. These waves carry energy and information about violent events in the universe. The early universe itself also carried something like sound. Shortly after the Big Bang, the cosmos was filled with a hot, dense plasma of particles and radiation. In that early state, matter and light were tightly coupled, forming a fluid-like medium. Tiny fluctuations in density created pressure waves that traveled through this plasma. These waves are known as baryon acoustic oscillations. They left subtle imprints on the distribution of galaxies that we observe today. In a sense, the universe began with a kind of cosmic symphony, ripples of pressure expanding outward in the first few 100,000 years. When a universe cooled enough for atoms to form and light to travel freely, those waves froze into patterns. The cosmic microwave background radiation still carries traces of these primordial oscillations. By studying them, scientists learn about the composition and evolution of the cosmos. Even though we cannot hear these ancient vibrations directly, they are echoes from the earliest chapter of time. Closer to home, our own sun produces waves and oscillations. The surface of the sun constantly vibrates due to convection and magnetic activity. Scientists study these vibrations in a field called helioseismology. By analyzing how waves move across the sun's surface, researchers can probe its internal structure, much like seismologists use earthquakes to study Earth's interior. Stars throughout the galaxy also pulsate, expand, and contract, generating rhythmic changes in brightness that reveal their internal physics. In this way, the universe is filled with signals, rhythms, and patterns that resemble music, though they exist beyond the range of human hearing. Sound in space is therefore not absent. It is transformed. It exists in plasma waves, magnetic oscillations, gravitational ripples, and electromagnetic frequencies. The silence of space is only silence to human ears. Beyond pressure waves and plasma, the universe also contains gravitational waves, ripples in spacetime itself. Predicted by Einstein's theory of general relativity, Gravitational waves are produced when massive objects accelerate, especially during extreme events like the collision of black holes or neutron stars. When two black holes spiral toward each other, they generate waves that propagate outward at the speed of light. These waves stretch and compress spacetime as they pass. In 2015, humanity detected gravitational waves directly for the first time, using instruments capable of measuring distortions smaller than a fraction of a proton's width. When scientists converted those signals into audible frequencies, they produced a brief chirp, rising in pitch as the black holes merged. This was not sound traveling through air. It was a translation of space-time vibrations into something our ears could interpret. In a profound sense, we heard the universe for the first time. The idea that space-time itself can vibrate challenges the notion of silence. Even in a vacuum, the fabric of reality is dynamic. Solar wind interacting with planetary magnetic fields can also generate radio emissions. Jupiter, for example, produces powerful radio waves that can be converted into eerie sounds. These emissions are caused by charged particles spiraling along magnetic field lines. Spacecraft have recorded such signals and translated them into audio, revealing strange whistles and bursts that sound almost otherworldly. These recordings are not conventional sound waves, but electromagnetic emissions transformed into audible form. They reveal that planets and stars are not mute objects. They emit energy across the spectrum. The boundary between silence and sound becomes blurred when we consider that our perception depends on biology. Human ears evolved to detect vibrations within a narrow frequency range. But the universe operates across an enormous spectrum, from low-frequency gravitational waves spanning light years to high-energy gamma rays. If we possess different senses, we might experience space as a constant roar of activity. The concept of silence in space is therefore relative. It is silence only within the limits of our hearing. Even in the emptiest regions, quantum mechanics suggests that fluctuations occur. Virtual particles emerge and vanish in what appears to be empty vacuum. On the smallest scales, the universe may never be truly still. The vacuum itself contains energy. This means that the deepest silence may still conceal subtle motion. The universe, from its earliest plasma oscillations to its modern gravitational waves, is filled with patterns of vibration. It may not produce sound in the cinematic sense, but it resonates in ways that science continues to uncover. When we say space is silent, we speak from the perspective of air-breathing creatures evolved on a planet. When we say the universe vibrates, we speak from the perspective of physics. Both are true. Space does not carry sound as we know it, yet the cosmos is far from quiet. It pulses with energy, ripples with gravitational waves, hums with plasma oscillations, and echoes with the relic vibrations of the Big Bang. The silence of space is not emptiness. It is transformation. It is the absence of air, not the absence of motion. And as our instruments grow more sensitive, we continue translating these cosmic vibrations into forms we can see, measure, and even hear. In doing so, we expand our senses beyond biology, allowing humanity to listen to a universe that was never truly silent.